Hello everyone and welcome to lecture. Today's lecture will be about infinite series and some specific examples of infinite series and how to tell if they converge or diverge. So an infinite series can loosely be thought of as an infinite sum of numbers. And we already have a nice natural notation for summation from our previous discussion on Riemann sums. Specifically, it's the sigma notation, which stands for the sum starting at k equals some value p of some sequence ak, but an infinite series, unlike a finite series, where it's a sum from, say, k equals 1 or p, some value, starting value, up to a finite number n. An infinite series is actually a sum of infinitely many things. It just keeps going. And initially, this poses a pretty severe problem for us in terms of actually defining, right, whether this makes sense or not. Because, for example, if I were to consider one of our previous examples that made a lot of sense, remember that when we sum from 1 to n of just the integer k, so this is 1 plus 2 plus 3 plus 4 plus 5, and ending at n, we were able to show that this is the same thing as n times n plus 1 over 2 for any integer n. However, this is definitely not an infinite series that will exist in what's called the traditional sense, or the convergence of the series sense, which we'll define a little bit later on in the lecture. Right, if we think of this sum from 1 to infinity, this is like saying 1 plus 2 plus 3 plus 4 plus 5 plus, and so on and so forth. This very clearly is not converging. It's getting larger and larger and larger and larger, and going to positive infinity as the number of terms in the sum gets larger and larger and larger and larger. So we'll make this a little bit more clear later on in the lecture, and more exact later on in the lecture. And the first thing we need to do is define this. Now, it's also interesting to point out that there actually are ways of making sense of a series of this form. They're it's a very, very advanced method using very advanced complex analysis ideas. There's an idea in complex analysis called Riemann Continuation. And the idea is that these sums can, in fact, be given values and identified with certain values, but in a traditional convergence sense, the sense that we're going to define in shortly, it's not possible to say that this converges. This value very clearly is getting larger and larger and larger, but it still is possible to identify a given series with certain weaker types of convergence and weaker types of identification. So if you want to learn more about that, let me know. I can talk to you about that. It's definitely a very advanced technique in mathematics, but it has a lot of applications in quantum mechanics and other fields as well, which is very cool. But for now, we're just going to stick with the classical analysis definition of convergence and divergence of a series. So the big question is how to define convergence and divergence of an infinite series. And the main way forward for this is going to be the following. We are going to pull on our information from sequences, for sequences. Specifically, we know the definition for the convergence of a sequence. So what we're going to do is determine a very special sequence that's related to a given series. And this is called the sequence of partial sums. And simply put, we call this sequence of partial sums Sn, or the sequence S1, S2, S3, and so on and so forth, all the way up to Sn. But it's an infinite sequence, so it keeps going on. And the way that we define the terms in the sequence is we just say that the nth term, or the kth term, I think I'll go with the nth term, because we have Sn right there. The nth term in the sequence of partial sums is just the sum from k equals 1 to n of ak. So the idea is that for a given series, or a given infinite series, the sequence of partial sums associated with that series is the sequence of sums of the first n terms for the nth element in the sequence. So remember, this summation notation is saying that this is a1 plus a2 all the way up to an. And we say that if the sequence of partial sums converges, or has a limit, in our other sequence definition of the limit, so according to the sequence definition of the limit, remember this is the sequence of partial sums, Sn. If this has a limit, then the infinite series is said to converge. And the value that that limit converges to is the value, we call it, of the infinite series. Conversely, if the sequence Sn, or we'll say if the limit of the sequence Sn does not exist, then the infinite series is said to diverge. So simply put, we just use the definition of convergence of a sequence to define what it means for an infinite series to converge. Specifically, we look at a very specific sequence, this sequence of partial sums. So like the first term in this sequence is a1, the second term is a1 plus a2, the third term is a1 plus a2 plus a3, right, and so on and so forth. So what we're saying is that if this limit converges, or if this sequence converges to a limit, then the series is said to converge. And if this sequence does not converge to a limit, the limit does not exist, so it blows up to positive infinity or oscillates infinitely, then the infinite series diverges. So we have three main computation rules that very nicely kind of follow directly from our rules for sequences as well. You can go through and take all of the rules from sequences and think about how to apply those to the sequence of partial sums. So I'm going to list these right now, just so that we have a list of the three main computational tools. So all of this is assuming, so if we have two separate convergent infinite series, right, then we can add them together. So we have a sum rule, which basically means that if you take the summation from k equals 1 to infinity of ak plus bk, we'll call this these two convergent series. We'll assume that one series, say, converges to capital A, which is the sum from k equals 1 to infinity of ak, and we'll say that b is the sum from k equals 1 to infinity of bk. So this shows that the sum of ak plus bk is going to be the sum from k equals 1 to infinity of ak plus the sum from k equals 1 to infinity of bk, which is just going to be a plus b. We also have a difference rule, which is very similar to the sum rule. It allows us to say that the sum, the infinite sum, if it exists or converges, of ak minus bk is the same thing as the infinite sum of ak minus the infinite sum of bk, which is just going to be the limit a minus b. And then lastly, we have the constant rule, or the constant multiple rule. And this says that the sum from k equals 1 to infinity of some constant c times ak is the same thing as that constant times the sum from k equals 1 to infinity of ak, which is equal to c times a. So these three rules are all very relatively basic rules and can all be shown to hold in using the definition of what it means for a series to converge. So just by focusing on the limit definition of convergence of an infinite series. The last basic rule that we have, and really I'll probably call this not a rule but a basic convergence theorem, because one of the big topics of this lecture is going to be the convergence theorems for positive series, is what's called the nth term test, or the nth term convergence theorem. So it's the nth term test for convergence of a series. And basically what this says is that for a series an infinite series of the form sum from k equals 1 to infinity of ak if the limit as k goes to infinity of ak is not equal to 0. If this limit of the terms in this series is non-zero, then the series has to diverge. This is essentially saying that if the terms in the series are not going to 0, there's absolutely no possibility of the series converging. And we'll see in a second that this does not necessarily mean that if the limit is equal to 0, then the series converges. This is not true. The only thing that the nth term test tells us is that if the limit of terms in the series is not going to 0, then the series has to diverge. It cannot converge. It's impossible for it to converge. So this is a very important test. So one of the most important series to consider is the P series. And this will be shown to converge a little bit later on in the lecture, but the idea is that this converges for fixed values of P. So P series is any series of the form sum from, we typically started at 1, from k equals 1 to infinity. You could start it at higher values of k as well, but it's the sum 1 over k to the p. So any series of this form is a P series. Where P is a fixed real number. And typically P is a positive real number. Because if it's a negative real number, we can very clearly see that you'll be summing something that gets very, very large or very, very fast. So it will definitely diverge. So a good example of P series is saying we'll just take P equals 2. So this is like saying 1 over 1. So it's 1 plus 1 over 2 squared, or 4, plus 1 over 3 squared, or 9, and so on and so forth, all the way to infinity. And it turns out that with there are a couple different methods to actually show. It's not easy, but it's a couple different methods that we can show that this actually converges to the value pi squared over 6. But the series with p equals 1 or the sum of 1 over k diverges. This is actually called the harmonic series when p equals 1. A P series with p equals 1 is the harmonic series. This is the sum 1 plus 1/2 plus 1/3 plus 1/4, and so on and so forth. So the main idea that we're kind of seeing here is that for a given series of a very relatively simple form, we have very different possible cases. You can have that the series very heavily depends on how it's kind of constructed, depending on whether it's going to converge or diverge. Right? This is the P series for p equals 2 converges, but the P series with p equals 1 diverges. These are two really good examples kind of showing that you have to be very, very careful when we're talking about a given series. Even for a series of the same form, mathematically, it may converge for certain values of how it's defined, or the certain values of the parameter it's defined with, and it may diverge for others. So you have to be very, very careful. What we'll see when we do the integral test is that a P series converges if the p-value is a value strictly greater than 1. And I'm stating this here without proof, but we'll show this when we get to the integral test. So this p-series is also a very good example of the nth term test, and showing how just because the terms in a series are going to 0, that doesn't necessarily mean that the series converges. Right? This first example here, the limit of terms in this series as k goes to infinity of 1 over k squared is equal to 0. So the terms are going to 0 and the series converges. But for the harmonic series, you also have the limit of the terms in the series is the limit as k goes to infinity of 1 over k, which is also going to 0, but this series still diverges. This is a great example of how not to use the nth term test. So you can't use the nth term test. You can only use the nth term test to say that if this limit of terms in the series is going to 0, or is not going to 0, so it's a non-zero value, then the series has to diverge. It doesn't tell you anything about a series if the limit of terms are going to 0. Another interesting series that we can consider and will be very important to us. The p-series is very important for a number of different reasons. Another very interesting infinite series that we can talk about is what's called a geometric series, or the so-called infinite geometric series. So you recall that a geometric series, we talked about finite geometric series way back when we did Riemann sums, is a series of the form it starts at k equals 0, and it sums to infinity, and it's a series of the form a, where a is a real number, times r to the k. When you plug in for the actual terms of the series, you get a times r to the 0, which is a times 1, or a, plus a times r to the 1, plus a times r squared, and so on and so forth, all the way to infinity. So it turns out that we kind of already have the tools at our disposal to figure out what this actually converges to and why it converges. So we know that for a finite geometric series from before, we showed that a finite geometric series is the sum from k equals 1 to n, so some finite value n, of a times r to the k. And one of the things we showed is that this series, it starts at 0, should start at 0. This series right here will always converge to a times 1 minus r to the n plus 1 over 1 minus r. This is a formula that we proved back when we did the summation notation for Riemann sums. And the idea here is that, well, this is exactly how we get our sequence of partial sums for the infinite geometric series. So that the sequence of partial sums for the infinite geometric series can be directly obtained using this direct closed form formula for this sum right here. What's nice about our definition of how we've defined infinite series convergence is that the for this limit, or I guess for this sequence of partial sums, the infinite series has to be equal to the limit as n goes to infinity of this Sn, if it exists. So this limit as n goes to infinity is going to be the following. It'll be the limit as n goes to infinity of this a times 1 minus r to the n plus 1 over 1 minus r, which is the same thing as a over 1 minus r times the limit of 1 as n goes to infinity, which is just 1, minus the limit as n goes to infinity of r to the n plus 1. And you see that this is going to exist as long as the absolute value of r is less than 1. If the absolute value of r is greater than 1, then this limit will be positive infinity. But if it's less than 1, then this limit exists and is in fact just equal to 0. It's like taking the limit as n goes to infinity of, say, like 1/3 to the n plus 1. This will be equal to 0 because the power of 1/3 gets smaller and smaller and smaller. This is true for any number that's between -1 and 1. So this limit exists only when r is between 1 and -1. It's a small enough number. If this is the case, then this limit is equal to 0. And we have the limit of this sequence of partial sums is just a over 1 minus r. So for any value of r, the infinite geometric series, or any value of r in this interval, the infinite geometric series converges to a over 1 minus r. And you might also ask, why couldn't r equal 1 or be equal to 1? And the main problem here is that in this case we're dividing by this 1 minus r. So you run into a little bit of a limit issue that you have to deal with. And sure enough, if r is equal to 1, right, I think the easiest thing to look at is the series itself. You get the sum of a plus a plus a plus a plus a. Or if r is equal to -1, you get a minus a plus a minus a plus a, both of which are divergent series. So r really cannot be equal to 1 or -1 either. This formula only holds if r is strictly between -1 and 1. This is a very, very useful tool. The p-series and the geometric series actually form, in some sense, the foundation of what we're going to be doing in a few lectures, which is defining the p-series, or defining not the p-series, the power series, and then using this for the results for power series on what are called Taylor series. So we can go back to, say, the concentration example from before, and recall that for the concentration example, we showed that the explicit form of the concentration series for the concentration CK was given by the sum from I equals 0 to k of the initial concentration times 1/2 to to the k, and we can immediately use our formula for geometric series. You recognize that this is in fact a geometric series, and thus the concentration is going to be the final concentration at infinity after infinitely many doses is going to be 1 C naught over 1 minus 1/2, because our R value here is equal to 1/2, which is going to be C naught over 1/2, or 2 times C naught, which is exactly the limit that we got using the recursive sequence. This is now kind of using series to solve for that limit, which is very, very cool that we can do that. So another example. Take the sum from k equals 1 to infinity of 3 over 4 to the k plus the sum from k equals 1 to infinity. Actually, what we'll first do is just say, let's say we just kind of consider this sum, the sum of this 3 over 4 to the k plus 1/2 to the k. Well, we note that if these are two convergent series, this is going to be the same thing as the sum from k equals 1 to infinity of 3/4 to the k plus the sum from k equals 1 to infinity of 1/2 to the k from our sum rule, if both of these are convergent. And they actually are convergent, because this series right here is a geometric series with r equals 3/4, which is less than 1. And this series right here is also a geometric series, but with r equals 1/2, which is another value that's less than 1. You also have to be careful here. Both these series are starting at k equals 1. So we'll call this first sequence the A sequence. Right? If we know that the sum from k equals 0 to infinity of 3/4 to the k is equal to 1 over 1 minus 3/4, which is 1 over 1/4, or 4. And likewise, we'll call B the sum from k equals 0 to infinity of 1/2. This is going to converge from our formula to 1 over 1 minus 1/2, or 2. So the last thing we need to do when we're computing this sum right here is notice this, and notice that, well, this is starting at k equals 1, which is the sum of the k equals 1 term, second term in the series, third term in the series. What we have to do is subtract out the 0th term in the geometric sum. So this is going to be the value of the sum from k equals 0 to infinity of 3/4 to the k minus the first term in the series. Same thing with this expression right here. This is going to be the sum from k equals 0 to infinity of 1/2 to the k, or the b value. So this is going to be 2 minus the first term in the sequence, which we'll call b0, b0. So it's a minus a0 is 3/4 to the 0, which is 1. b0 is 1/2 to the 0, or 1. This is going to be 4 minus 1, which is 3, plus 2 minus 1, which is 1. So ultimately, this series, we've shown, converges to 4. This is a good example for a number of reasons, but the main idea here is that it shows us that we can apply our geometric series formula even if we don't start at k equals 0. This would have to be done, say, if you start at k equals 2, k equals 3, you always have to subtract out the first couple terms if you start at a higher value of k. So the main couple tests that we have for convergence can be directly summarized and used to show convergence of a given series. And these are actually, in some sense, the first two of these are very, very similar to our tests for improper integrals. The direct comparison test for series is the following. So it's called the direct comparison test and the limit comparison test, just like our tests for improper integrals. And this says the following. It says that suppose that the sum of some series ak from k equals 0 to infinity is it could be possibly complicated. It could be very, very complicated. And usually it is when we're forced to use one of these comparison tests. So we're looking to find the convergence of this series. And one of the key assumptions of the direct comparison test is that the terms in the series all have to be greater than or equal to 0. They all have to be positive. And we also have to assume, say, that we have another series, bk, that is above ak, and a series ck that is below ak. So we have to have the terms in the individual series are for ak, say, is going to be bounded above by bk and bounded below by ck. So the direct comparison says the following three things. It says that if the sum from k equals 0 to infinity of the bk's converges, then the sum of our unknown series ak also converges. And that's from this inequality right here. If it's basically saying that if you have a whole bunch of positive values and bk's are always greater than or equal to the ak's, and the top sum converges, the things that are greater than ak converges, if you add them all together, then the sum of the ak's also has to converge. Likewise, if the sum from k equals 0 to infinity is separate from this one right here, so let's assume instead that the sum of the lower series diverges, then the divergence of that lower series of positive sums forces the more complicated series of ak's to also diverge. So this is the key points in this direct comparison test. So you can use these tests similarly to how you used it for the improper integral, this direct comparison test, which is a very, very nice tool. It's a extremely powerful tool for telling us, for very complicated sequences and series, whether the series will converge or diverge. If you can find a nice comparison series that is simpler to investigate the convergence of or divergence of. The second test that we have is the limit comparison test. In the limit comparison test, the assumptions are relatively similar to the direct comparison test. We have a series with positive values, all positive values, and we also have this series is a series of positive values, and we're again investigating the convergence of this series. You can start at 0 if you want, but I'll just write it similarly to before. Start at k equals 1. So we're investigating the convergence of this series. And the limit comparison test is a very similar statement to the limit comparison test for improper integrals. It says that the following. So suppose that we can find a comparison series we'll call this the sum of bk. This is our comparison series. That in general, right, the more complicated series is AK. This is the one that we're investigating the convergence of. So we want to find a comparison series that's simpler to investigate the convergence of. Such that the limit as k goes to infinity of the ratio of AK over BK is equal to L. Notice that this is exactly the same limit in some sense as the limit we got when we did the limit comparison test for improper integrals. And now this is for series. Well, we have a couple different conditions if on the value of L. So the first one is directly related to the result of the limit comparison test for integrals. If this limit is between 0 and positive infinity, so it's a real number that's greater than 0 but less than positive infinity, then the sum of AK and the infinite sum of BK both converge. So either both converge or they both diverge. And so if the limit of the ratios of the terms in these series is equal to a real number, a positive real number that's between 0 and infinity, then the AK series has to do the same thing as the BK series, which means that BK is a simpler series than AK, so it's easier to evaluate the convergence or divergence of it. And the idea is that if you can show that BK diverges, then AK must also necessarily diverge, and vice versa. We also have a couple more results. The limit comparison test actually tells us some more things about even if the limit is equal to 0 or the limit's equal to infinity. It's a little bit weaker, but it says that if L, this limit, is equal to 0 and BK converges, then it says that the AK must also converge. So unlike the limit comparison test for improper integrals, we have a little bit more that it tells us. So this limit tells us a little bit more about what's going on with these two series. Doesn't say anything about divergence if the limit is 0, but if the limit is equal to 0 and you know that BK converges, then you can conclude that AK must also converge. And likewise, if this limit is equal to positive infinity and the sum of the BK diverges, then this implies that the sum of the AKs must also diverge. And the main justification for all of these is essentially looking at a comparison in what this limit is telling us about the series itself. In the final case, right? If this limit's equal to infinity, that means that the terms of BK are growing in some sense much slower than the terms of AK, because if this limit of the ratio is equal to positive infinity, then that means that this is a large number in general for large values of k, because this limit's going to positive infinity, say, for this third case, in which case BK is growing a lot slower than AK is. So if BK diverges and BK is growing much slower than AK as k gets larger and larger and larger, this series blows up. A similar argument can be made for the case of L equals 0. Right? If L equals 0, then that means that this limit's going to 0, so the BK series is getting larger and growing much faster than the AK series. So therefore, if the BK converges, that also must imply that the AK converges as well, because AK is growing slower than BK in the second case here. The first case is a very, very similar argument, that if this is any real number that's between 0 and infinity, right, then essentially for large values of k, AK is approximately equal to L times BK for very large values of k. And that's sort of a very quick justification. It isn't not a full proof, but the idea is that this is how you would prove this result. So these are two of the main tests that we can use for proving and showing convergence of positive series of numbers. The last test that we have is called the integral test. And this is the final test that we'll look at for positive series. So the integral test says the following. It says that so we'll suppose we have a series. So we don't know if the series converges or not. We'll say we sum the series from n to infinity, and we're investigating the convergence of this series. And furthermore, suppose the following. Suppose that the sequence ak that is giving the terms in this series is given by a function. So we know the explicit form of ak, say, is ak is equal to, we'll say ak first of all they all have to be positive. The series has to be positive. We'll say ak is equal to some function of k. So we have the function that's giving the explicit form of the terms in this series. So we're going to assume a couple assumptions on this function f. Say if it has to be continuous. So it's a continuous function. Well, it has to be a positive function because of this condition. And lastly, it has to be a decreasing function. So the derivative of f has to be less than 0 for positive values of x. So on the domain that we're considering, if these three things are true about this function, then the integral test says the following. It says that, so if all of this is true, then we have the following. The series of ak and the integral, the improper integral from n to infinity of the function f of x dx either both converge or diverge. So what this tells us we can do is that if we have an unknown series, we don't know if it converges or not, we can, instead of just looking at the series, look at the improper integral of the function that's generating the terms in this series, and compare this improper integral to the series itself. Now, it doesn't tell us that they converge to the same value. That's definitely not true. However, you can get an error estimate of from this process, this formula. Specifically, if you take any series and you say, let's say we go up to some fixed value. So let's say we take the series k equals n to ak, this infinite series. And we decide to look at stopping this sum at some point. So we say consider the sum of the first n, capital N, up to capital or lowercase n terms of the series. This infinite sum of ak is going to be the sum from lowercase n, or from capital N to lowercase n, plus the sum from k equals n plus 1 to infinity of ak, where this term is sometimes called the remainder term. And we'll call this Rn. So it's the sum from n to n of ak plus the remainder term, which is actually, it's an error term in this expression. Because if we truncate the series, if we don't sum it all the way to positive infinity, you're going to have that this sum is going to be the sum of the terms from capital N to lowercase n plus this extra term, which is the error. It's like the sum of all the things past n, which is why we call it Rn, or the remainder. One of the things that we can do when we go through and actually prove the integral test is that we can prove that the remainder term Rn will always be bounded above and bounded below. It's bounded above by the improper integral from n to infinity of f of x, and it's bounded below by the improper integral from n plus 1 to infinity of f of x dx. It's a very useful tool because it actually allows us to tell us, it tells us how many terms we have to go out into a given series like this that is to get a certain error. If you want to bound, say, the error Rn by a certain value, you can definitively do this, which is very, very, very cool. So these are the three main convergence tests that we have for series, and they help us if we have a given series. We can use any of these tests to determine whether or not a given series will converge. So let's apply this to the P series to get that result that we mentioned earlier in the lecture. So the P series is the sum from k equals 1 to infinity of 1 over k to the P. What that means is that right, this is our kth term in this series. So the function f of x that's generating this term is the function 1 over x to the P. This function is continuous for x greater than or equal to 0, or it's greater than or equal to 1. It is decreasing. We take the derivative of this function, you get that f prime of x is going to be negative p times 1 over x to the 1 minus p. So this is the derivative of this function. Oh, sorry, it's x to the 1 over x to the p plus 1, or x to the negative p plus 1. And this function is always negative for any x values that are positive. Therefore, this is a decreasing function when x is greater than or equal to 1. And it's positive. This function is the function itself is positive for x greater than or equal to 1. So this function satisfies all of the conditions of the integral test, which means that the improper integral from 1 to infinity of the function of f of x, which is 1 over x to the p, if this diverges, then this series also has to diverge by the integral test, and if it converges, then this series has to converge. So we know how to get the convergence or divergence of an improper integral. This is the limit as b goes to infinity of the antiderivative, or the definite integral from 1 to b of 1 over x to the p, which is x to the negative p. And this antiderivative is equal to the limit as b goes to infinity, then this antiderivative, which is going to be evaluated at b and 1. Antiderivative of this is going to be 1 over negative p plus 1 times x to the negative p plus 1 evaluated from b to 1. And this then becomes the limit as b goes to infinity of 1 over 1 minus p times b to the 1 minus p minus 1 to the 1 minus p, or just 1. Now this antiderivative right here, this is for when p is strictly greater than 0, or greater than not equal to 1. Sorry. So this antiderivative is when p is not equal to 1. If p is equal to 1, then you have a slightly different antiderivative. You have that this is the limit as b goes to infinity. So you have two separate possible values for this antiderivative corresponding to what p is. So the limit as b goes to infinity of the antiderivative of this function. When p is 1 here, you have the antiderivative of 1 over x, which is just the natural log of the absolute value of x from b to 1, or the limit as b goes to infinity of natural log of b minus the natural log of 1. And this limit, because the natural log of b is equal to negative infinity. So this diverges if p is equal to 1. That's this first piece of this integral when p equals 1. And for any other value of p, this is the antiderivative. This is p is not equal to 1. So this path corresponds to. And this limit only exists as two possibilities. If p is less than 1, or if p is greater than 1, strictly greater than 1. And if p is less than 1, then the exponent of p here of b is positive, because you have 1, or b to the positive number, which means that this limit's going to be positive infinity. And if p is greater than 1, then the exponent of b is negative, because you have 1 minus a number that's greater than 1. Therefore, this limit of b is going to be 0, and this integral is going to be negative 1 over 1 minus b, or 1 over p minus 1. So in short, the improper integral from 1 to infinity of 1 over x to the p dx only converges, and we've seen this before, but I'm doing this again just to show you how to quickly go through and do this, only converges if p is strictly greater than 1, and it diverges otherwise. So it diverges when p is less than or equal to 1. And what that implies for us is directly that by the integral test, that the p series diverges when p is less than or equal to 1, and converges when p is strictly greater than 1. So this is kind of cool example, because it shows you the power of this integral test. If you can do the improper integral, you can go through and investigate many different series. And this gives us both of the two results talked about before, as well as a number of other results. So if I ask you, say, about the convergence of the series 1 over square root of k, and k equals 1 to infinity, right? This is going to diverge because it's a p series with p equals 1/2. So by the integral tests that we showed before, this has to diverge. Whereas, if we take the series of from k equals 1 to infinity of 1 over k squared, the cube root of k squared, this is also going to converge, or it's going to diverge. But let's say we change this a little bit, so we get another convergence series. The square root of k cubed. This series is going to be the sum from k equals 1 to infinity of 1 over k to the 3/2. This is going to converge because p is equal to 3/2, which is a number that's greater than 1. Now be careful. This test doesn't tell you that it converges to the same value as the improper integral. So we don't know in general what the value it converges to is. And in general, that's a very hard thing to evaluate. But we saw that you can do an error estimation, and if you know it converges by the p-test, then you can say that this remainder term, for stopping at some n value, will always be less than or equal to and greater than or equal to two different improper integrals. So just because we can't find the exact value, we can say how far out you need to go in the series to bound this remainder term, right? And this result is relatively straightforward to evaluate because we already know what this improper integral is going to be. In general, from 1 to infinity, the process is very, very similar for from actually any value to infinity, right? The improper integral of this function from, say, a to infinity is the limit as n goes to infinity of the improper integral from a to b. This is from as b goes to infinity of 1 over x to the p dx, which is the same thing as the limit as b goes to infinity of the antiderivative of this, which is 1 over 1 minus p times x to the 1 minus p from b to a. So for any starting value a, for positive starting value, this will be the same thing as 1 over 1 minus p times the limit as b goes to infinity of b to the 1 minus p minus a to the 1 minus p. Where the limit as b goes to infinity of this is going to be 0 when p is greater than 1. So this is just going to be equal to negative a to the 1 minus p over 1 minus p, or a over a to the 1 minus p over p minus 1. So what this tells us about our remainder is that the remainder for this series will always be less than or equal to, it'll be n to the 1 minus p over p minus 1, and it'll always be greater than or equal to n plus 1 to the 1 minus p over p minus 1. So we can do cool things where we can ask questions like, how far out in the series do you have to go to bound the remainder less than a certain tolerance? Let's say you have some error tolerance and you want to figure out how far out to go in the series to bound maximum error. So we'll say the error tolerance is equal to epsilon, say. You want to make sure that this remainder term is less than this epsilon. So if we want to do that, we have to make sure that Rn, which we know is less than or equal to n to the 1 minus p over p minus 1. To do this, we have to guarantee that n is chosen to be a large enough value such that this is less than that error, we'll call it epsilon. So to figure that out, you can say, well, the boundary of this inequality happens when n to the 1 minus p over n minus 1 is equal to epsilon, or n to the 1 minus p is equal to n minus 1 times epsilon. And if you can solve this equation right here for n, and that'll guarantee you to choose an n that will be satisfy this inequality right here. Right, so it'll be it gives you a direct method of choosing where to stop in the series to guarantee a certain error tolerance for the remainder, which is very, very cool. But that will conclude today's lecture. Thank you very much for tuning in. I hope you learned something and had a great day.